Thank you, everyone. Welcome to the third SNAPP seminar of this spring. My name is Changhan Ri. I am chairing SNAPP seminar series, the organizing committee of the SNAPP seminar series this academic year. And it's my great pleasure to have Yuxin Chen today. So Yuxin is currently an associate professor at in the statistics and data science, as well as electrical and systems engineering at the University of Pennsylvania. And before joining UPenn, Yuxin was an assistant professor in electrical and computer engineering at Princeton. He received a PhD in electrical engineering at Stanford, and he also was a postdoc at Stanford Statistics. Yuxin's current research interests include high-dimensional statistics, non-convex optimization, and machine learning theory. So he received Alfred Sloan Research Fellowship, the SIAM Activity Group on Imaging Science Best Paper Prize, ICCM Best Paper Award Gold Medal, and he was also finalist for the Best Paper Prize for Young Researchers in Continuous Optimization. And he was also a Princeton Graduate Mentoring Award. He also received Princeton Graduate Mentoring Award. So today I'm excited to learn from Yuxin about extremely timely topic on the diffusion models. So without further ado, the stage yours.
Okay, thanks a lot, Changhan, for the very kind introduction. And also thanks for the committee for inviting me to present my work in this exciting seminar series. So my talk today is about some of our recent progress towards understanding and also accelerating diffusion models, one of the most popular way to do generative modeling in the last 2 to 3 years. My former colleague, Mondi Wang, actually has given a very nice talk a few weeks ago about diffusion models as well. So she has already set up the background a lot for me, so which make it easier for me to go into the math part. So all right, so this talk is mainly based on joint work with the following collaborators. In particular, my former postdoc Li, who just started his faculty job in CUHK, current student Yu Huang, and also in collaboration with Timothy Yue from Carnegie Mellon and my colleague Yu Ting at Penn. And by the way, if you have any question, feel free to interrupt me anytime. I don't really have to finish all the slides here. I'm hoping to make things more engaging. All right. All right. Okay. So we have, in some sense, already entered the era of generative AI, at least starting from the advent of ChatGPT. So it comes as a surprise that generative AI can transform our daily life so quickly. So we have now new large models coming, being released once every few days. And they are able to do so many things, and they can generate images, generate videos, generate codes, produce music, so on and so forth. And so it has really been everywhere this year in everyone's lifetime. So when I talk about generative model, it will probably be good for me to try to make it slightly more formal here, just in case you are not yet super familiar with this topic. So suppose that you have a target data distribution or target data set, or sometimes it's used as a training data set. So think about a large set of images of horses, all right? So each of them might be drawn from some target data distribution. So let's call it P data here. All right. So each of the images might be high dimension. So it might be D-dimensional data where D could be large. A P data or target distribution could be something that's fairly general. Okay. So what generative models is trying to do is that, okay, so after you see the large training data sets, we ask an algorithm to generate a new sample. a new sample that's not really like something that you just redraw from the existing training data set, but really something that looks very new, but also it looks like it is a new independent sample drawn from the target data distribution PDA. So think about the things that you're trying to draw a fake image, pause, but it looks almost indistinguishable from what you have already seen from the training data set. Okay, so this is what generative model in general is trying to do. And there have been a lot of exciting progress in the last 10 days, over the last 10 years about generative modeling. Some of the most famous examples include generative adversarial network scan and VAE variational autoencoder. More recently, one new generative model called diffusion model has underpinned the major success in the generative AI in the past 2 to 3 years. And as Mondi has already talked a lot about, just to remind you, it has a lot of applications across a lot of different domains. Like DALL-E 3, which has been used to generate new images. Sora, which has been released fairly recently, which allows you to generate new videos. It has also been used heavily to aid in protein design, those kind of things in computational biology. So it really has found a large amount of applications across multiple domains here. Even though this actually is something that's originally inspired by, some physics thing like thermodynamics, it has recently been popularized in the computer science domain. Okay. So because of the huge success of diffusion models, it motivates a lot of researchers from across different fields to try to understand the fundamental principles of diffusion models and then try to design algorithms that can exploit our fundamental principle, which can hopefully eventually inform practice. So our recent work is essentially motivated by this. We're trying to, shed some fundamental light into this new and popular algorithmic paradigms here. Okay. All right. Okay. So before I begin to talk about our new theory, new algorithms, let me try to start by giving you more backgrounds and also just more notation, just to make sure that we are on the same page. All right, okay. So diffusion models, in particular score-based diffusion models, usually comprises two processes, okay? One forward process and one backward process. The forward process is the following very simple stochastic process. I start from x naught, where x naught is, let's say, think about it as a random instance drawn from the target distribution P data, all right? And what I'm going to do next is that I'm going to keep adding noise to this random instance. One way to add, and you can choose a lot of different ways to add noise, and one way to do it is to just keep adding Gaussian noise. And eventually, as you progressively add more and more Gaussian noise there, eventually you sort of like almost erase all of the information content there. And when you end up with xt, when capital T is large enough, it sort of like becomes almost like a pure noise. So this is illustrated by this image sequence here. So this is a trivial process. And this is sort of like counterintuitive because this is not what we want to do. It starts from the data that we care about. It adds more and more noise to completely erase the data information content. This is not what we are interested in about. What we are interested in is actually a reverse process. So ideally, if you have some oracle that can do the reverse process, say, for example, if I start from this like a very noisy thing, which contains almost no information, if some genius or oracle who is able to sort of like reverse this forward process, and then eventually give you back the host, and that would be something that we are very interested in. Okay, right. But of course, this is in general, this is not something that's possible, right? If you already erase almost all the information content, you won't be able to like denoise it in the way that still give you back the original image, the noiseless image there. Okay, but what might be possible is other things. So instead of trying to get back this exact random instance, what you can potentially do is say, okay, let's try to exploit some of the fundamental properties about this forward process. And then if you are able to leverage these important ingredients there, then maybe if you next time, if you just start from some pure Gaussian, absolutely no information there, and then maybe you can learn a new process, which I'm going to call a reverse process, that can hopefully generate a new data, while in the same time, we make sure that this new data has almost the same distribution as the original target distribution. Right. So that is what we want. Okay, so this involves a lot of learning part here because it requires us to know more about the, like the fundamental ingredient of this forward process. But hopefully this is something that is doable. Okay. Now, I talk about some important ingredients here. So what would be the crucial parts that allows us to achieve this goal? And it turns out that one of the most important thing is called score function. Or more precisely, this is the Stein score function, not the Fisher ways of score function, which is like the gradient of the log of the marginal density of the forward process. So I have ST here. T means the t's time step. If you look at the marginal distribution of xt at the time t, if you compute the gradient of the log of this density, this will give you the score function. So suppose that now you have access to the score function across all the time steps, then it turns out that it is feasible and it's probably feasible to generate a reverse process that achieve the following goal, in the sense that we can make sure the reverse process and the forward process actually have the same or almost the same marginal distribution. And that is what we want. Okay. All right. Okay. So now why this is okay. So as I mentioned, score function is the most crucial part, and I'm going to give you more precise details in 2 to 3 minutes. But because of the important thing about this, the importance of the score functions, the diffusion model, a lot of the diffusion model sampling mechanisms are usually called score-based diffusion models. And these kind of algorithms usually can be decomposed into two stages. In the first stage, I'm just going to look at the training data. And use a lot of training data to train the neural net, and that will help me get an estimate of the true score function. So ST here means the score estimate. Okay, it might involve a large neural net, which is usually hard to understand in theory, but this is what people do in practice. And this stage is often called score matching or score learning. Now, armed with the score estimate, the second stage is going to proceed as follows. You're going to design a backward process just by using this ST function, which I'm going to make precise in the next slide. And hopefully, just by doing so, you can generate maybe a stochastic process, maybe a deterministic process or something like that. But hopefully just generate a chain, and that eventually allows you to make sure that you have matching marginal distribution as like the forward process. And the second stage, we often call it data generation, sampling, things like this, okay? So in this talk, I'm going to focus primarily on the second stage. Okay, so when I talk about the second stage, now let me try to be more precise about what people have done. There have been a lot of algorithms there, as you can imagine. This is a popular topic. But there have been two algorithms that have been, at the core of this diffusion model things. The first thing is called a DDPM, or denoising diffusion probabilistic models algorithm. This is a stochastic approach. You are going to see why I call it a stochastic approach. It's the following. So there are different versions, like continuous time version, discrete time versions there. In discrete time, you can think about the sampler as following. I start from some pure Gaussian, Y capital T, okay? And from there, I'm going to keep updating and generate. So I'm working backwards, and then from YT, I'm going to generate YT minus 1, so on and so forth. And every time I'm generating YT minus 1, what I'm going to do is that I'm going to use YT and some additive noise. You generate some independent Gaussian noise. All right, okay, you pass it through some deterministic mapping. You carefully design one, and then that's going to be what you are doing. And more precisely, this is what DDPM is trying to do, is that the update rule consists of two parts. The first part, which is a deterministic component, which is a linear combination of YT and its score function. That is why I said score function is needed here. And I'm also adding another random component, so random Gaussian, and that, okay, so that becomes my sampler. Very simple one. It turns out to be very effective in practice. And later on, people realize that there's also a deterministic version based on the so-called probability flow ODE, which I'm going to explain in the next slide, is that the only difference between this and the stochastic version is that I'm not going to, so the same thing is that I start from the Gaussian noise, but throughout the rest of the process, I'm not going to add any further noise. Okay, so phi t now is a deterministic function. So every time after y capital T is determined, it becomes a deterministic process. Okay, that is why I said this is a deterministic sampler. So deterministic except for y capital T. And more concretely, this is like saying every single step yt minus 1 is just like a linear combination of yt and the corresponding score function. So this process is purely deterministic. Okay? All right, okay. So sometimes people also call it a DDIM algorithm. All right, okay. Now the question is why do we even believe that these two algorithms have some hope of achieving the goal that we set out to accomplish? There have been some nice interpretation from the continuous time limits, which let me just briefly mention to you. There will be quite a few equations here. You don't have to think carefully about what this equation really means here. I'm just trying to give you some idea about what people have done. Okay. So the forward process, even though I stated in the discrete time, if you pass it to the continuous time limit by, for example, taking the step size to be extremely small, it's well approximated by some stochastic differential equation, which takes this form. It can even be further generalized. Okay, so there is some SDE that allows you to capture the forward process. Now, the DDPM type algorithm, or the stochastic process, is based on the following observation. It's back in 1982 by Anderson, and he already showed that there exists a time reverse stochastic differential equation, which looks like this. You don't have to read what this is, but there is some reverse time SDE that allows you to make sure that this YT has the same marginal distribution as XT. In fact, it can be even more. It's not only marginal distribution, it can be much more than this, okay? But the existence fact is very important here. And the DDPM algorithm can essentially be viewed as some sort of like a discrete time version of this reverse time SDE, okay? Now, later on, people also realize that not only you can find an SDE that has this nice property, you can also generate an ODE that also has this property. Right? You start from, again, some random thing, and then you run an ODE, which people call probability flow ODE or diffusion or ODE. So something like this. Again, you don't have to read the equations here. But the nice thing is that this ODE also can make sure that the YT has the same marginal distribution as XT. Okay. Now, if you look at these two SDE and ODE, one interesting thing is that except for YT and potentially some Brownian motion or things like that, the only additional crucial part is this score function. And this, sorry, I forgot to say this QT means the marginal distribution of XT. So this is like a score function. In both cases, it involves score function. And that is why score function becomes one of the most crucial part for us to reverse the stochastic process. All right, okay. So this becomes a nice interpretation about how people come up with the DDPM and DDIM or probability flow ODE kind of algorithms. But in practice, there are things that are not readily explained by these two results. For example, you don't have perfect score estimates usually because this is learned from some training data set. You don't have perfect score function. You usually operate everything on the discrete time world rather than a continuous time world. You have some discretization because you want to use computers to help you do that. So these things might attribute to some of the source of the imperfectness of the data generation, which we'll also try to discuss here. All right, again, the key takeaway here is that if everything is perfect, if you have perfect score function, if you can already operate in the continuous time limits, things are so good. And the nice thing is that you almost have no restriction on the target data distribution. You don't need data distribution to be log-concave, smooth, things like that. You almost have no restrictions there, which actually is a very appealing thing for practical purpose, right? In practice, you're not really dealing with super nice distribution. You are dealing with super complicated one. So this becomes a nice part to start with. The question that we are hoping to understand more is that, first of all, this is actually the easier one. What happened in the discrete time if we come back from the continuous time world back to discrete time world? How will things change? How will the discretization error affect convergence? The other thing is that if we only have imperfect score functions, how will this affect the sampling fidelity? And these two things need some additional theory in order to understand. Okay, so and because of so far you probably have seen that the sampling part is extremely nice. It's very well formulated. Mathematically, it's very clean. And this sort of like gives us a sense that maybe some mathematical theory is possible. However, as I already mentioned, there is one stage that's very difficult to understand in theory, which is the score matching one. Because you usually involve training neural net, which is usually very hard to understand. So which make it very difficult to develop a full-fledged end-to-end theory for diffusion models. But the good thing is that if you are okay with doing some sort of like a divide and conquer kind of a strategy, but they completely decouple the score matching part and the sampling part, and then maybe there is something that you can say very formally and very relevantly for the generative sampling part. And this is what we are trying to do, and which is also something that has received a lot of attention in the last 1 to 2 years about the convergence theory about the sampling part, assuming some property about the score estimates that you already have. So in this talk, what we're going to do is the following. First of all, I'm trying to develop a new non-asymptotic theory for some of the most famous diffusion models in discrete time. And we're trying to develop a theory that hopefully can beat of the state of the art, which gives you a better understanding about what's going on there. And the next thing that we're going to do is that we're going to use our theory to think about whether there are ways for us to provably accelerate the diffusion model sampling part. And I'm going to mention later on that acceleration turns out to be one of the very, very important things in the recent research, both in theory and in practice. All right, okay, so let me start with the first part. All right, okay, so the first part is about a new non-asymptotic theoretical foundation for the DDIM and DDPM algorithms. In the interest of time, I'm only going to focus on the probability flow ODE part, the deterministic sampler, mostly because the stochastic one, actually people have other strategies to understand it in the almost tight optimal way. But the deterministic sampler has not been well understood until, at least our work. So I'm going to focus on this part first. But in our paper, we cover both of the algorithms. Okay, so let me just talk a little bit about the prior analysis for DDIM and also DDPM. There have been, as you can imagine, there have been quite a lot of work in the past 2 years. In particular, some MIT groups, some Harvard group, also Duke group, actually a lot of different groups and some European ones. And they have spent a lot of time thinking about the convergence theory about DDIM and DDPM algorithms. And typical strategy that they have been doing is that because of the nice property happening in continuous time limits, what they are doing is that usually I start with a discrete time world. I try to take a detour by making a connection between this and the continuous time limits. And there have been some nice toolbox from calculus, like from SDE and ODE toolbox that can help you understand what's happening in continuous time. And then they try to map it back to the discrete time world, and then by controlling the discretization error. So this has been the strategy underlying most of the prior works here. And it draws analogy from a lot of things coming up in different fields. For example, in reinforcement learning, when people analyze temporal difference learning, people try to think about it from the ODE perspective. When people try to analyze stochastic gradient descent or gradient descent, they try to resort to gradient flow or Wasserstein gradient flow as well. I mean, this has been a very common thing by resorting to toolbox in the continuous time limits. It has been very successful, at least in understanding the DDPM SDE type of algorithm. But unfortunately, the prior analysis, or at least the existing analysis, have been very inadequate for understanding the ODE type of deterministic samplers. I'm going to explain more details here, but just want to now tell you that there has been theory for the ODE type of sampler, but the analysis is very loose there. So which sort of like motivates us to think about whether there are other strategies for us to understand this, and also whether we can just think about things directly in the discrete time world rather than passing it to the continuous time limit. Right, for example, like in optimization, even though you are able to understand gradient descent through a detour to gradient flow, you don't really have to do it. You can actually, just by understanding gradient descent directly in the discrete time world. Both are useful, and you don't necessarily have to go to the continuous time. And this sort of like motivates our strategy here. So what we are going to do is that we're trying to develop a new non-asymptotic framework that can help us understand the discrete time process directly. And hopefully it can give us the best state of the best performance guarantees for both of the samples. Okay. All right, okay, so before I go to the details, I need to make some assumptions, right? I have imperfectness of score function, I have general data distribution, so at least I need to make a little bit of assumptions to make my theory precise. So the first assumption I'd like to make is about the target data distribution. Just to remind you, target data distribution is a distribution of X naught, or this P data thing. So I'm going to just make one assumption here, is that capital T is a number of iterations I have. I'm sort of like making assumptions saying that the size of the X naught with probability approaching 1 is bounded by some polynomial in T. Okay, and T is supposed to be something large. And this exponent CR can be arbitrarily large. Think about it as 100, something like that. All right. So I think in general, this means that the support size is allowed to be very, very large, and which essentially allows to accommodate most of the things happening in practice already. Okay. It's very general. It does not really need additional assumptions like log-concavity. It does not need you to assume some Lipschitz constant on the score function, things like that. All right, so it's very general. We try to make it very general. And in particular, if you are not happy with polynomially large size, just keep in mind the CR parameter. So eventually our iteration complexity is going to scale only logarithmically in the support size. So which sort of like means that things are going to scale very, very slowly as you increase the support size. So which is probably good enough for our practical purpose. Another set of assumptions that we have to make are on the score estimates. As I said, in general, we don't have access to perfect score function. We usually only have access to some noisy or imperfect, inaccurate score estimates there. So we have to make some assumptions there. So ST is our estimates. ST star is the true exact score functions there. So our assumption is the following. We are going to assume some L2 score functions there. And it's a mean square kind of estimation errors there, all right? Average across the T iterations there. So I'm going to use this new parameter here to sort of like do this. All right, okay. Now, this assumption in general is much less stringent than assuming some point-wise score estimation. Some people were going to say ST and ST star are closed in every single points there. We are not willing to make this assumption because that's usually too strong. We just want to say in some average L2 sense, they are close enough. Another thing that I like to emphasize is that actually this assumption alone already allows you to develop nice theory for the DDPM stochastic sampler. But unfortunately, this assumption alone, however small this epsilon score is insufficient for you often insufficient for you to develop a good theory for DDIM sampler. In particular, we can construct some counterexamples saying that even when the epsilon score is extremely small, the TV distance between y1 and x1 could still be close to 1, which means that it's not really useful. Okay, and that actually comes up because of the deterministic nature of the ODE type of sampler. In practice, it might still be very good. It's just that in theory, you have to preclude some of the counterexamples there. So in order to do this, we're going to make one additional assumption on the Jacobian of this. So we're going to say, if you look at the average error of the corresponding Jacobian error, they are also not going to be too large. Okay, so these two assumptions are what we make for the ODE type of set. Okay. So finally, I want to just briefly mention that we have a very concrete learning rate schedule in mind. Learning rate here, I refer to this beta T, which is the way that we construct the forward process. We are going to choose the learning rate in a very specific. Actually, our theory can accommodate a general learning rate, but by choosing the learning rate in this way, it sort of like gives you the fastest convergence. So it has two phases here. The first phase is that it's going to have some exponential increasing component here. So it's increasing fast at the beginning and then stay flat in the rest of the iterations. All right. It doesn't matter that much if you don't remember this, but I just want to tell you there's some sort of like a specific learning rate schedule that is studied here. And it also has been a common choice in other work, like in this Benton et al. For analyzing DDPM. Okay. All right, okay, so now I'm ready to move on to my theory here. So the theory is the following. Just to remind you, well, this YT minus 1 is the probability flow ODE algorithm here. So we are able to show the following. The probability ODE sampler achieves the following theoretical guarantee. So if we look at the total variation distance between x1 and y1, so essentially almost the starting points here, they are upper bounded by this way, where D is the dimension, capital T is the number of iterations, and these two epsilon quantities sort of like capture the score estimation errors. Some implications are in order. The first thing is about iteration complexity. So forget about those score estimation error parts. So let's assume we have perfect access to the score functions. This essentially is saying that if epsilon is small enough, the iteration complexity we have is roughly d squared over epsilon. I'm going to tell you how good this is momentarily. Okay, this is the first thing. The second message is that the algorithm is stable in the sense that the quality of this or the TV distance is proportional to the score estimation errors here. So essentially, it's that when your score becomes more and more inaccurate, the sampling fidelity will sort of like degrade gracefully. It's not going to degrade in a crazy way. All right. So this is one nice thing. Another thing is that again, it's important for me to stress that we are not making any assumption on log-concavity or the Lipschitz continuity of those, the forward process. We accommodate fairly general data distributions here. And finally, the D dependency, the dimension dependency here is not the optimal things that we want. Our ongoing work sort of like suggests that the correct dependency might be D over T rather than D squared over T. But since this is ongoing work, I'm not going to just give you a formal theory here, but our conjecture is that based on our ongoing calculation, is that it should be D over T here. And if this is D over T, I believe that this is the tight characterization of the performance guarantee. Okay, so this is our theorem, sort of like a easy, a simple theorem to read. What we can do now is maybe let's try to compare with prior work to see why our theory has any advantages compared to the prior theory. So the first theory that provides a comprehensive understanding about probability flow ODE is by Yuxin Chen and his collaborator last year in March around that time. So they provide the first polynomial time performance guarantee for this algorithm. There have been some advantages in our theory, which I'm going to explain. For example, this Chen et al. Actually, even though they have polynomial time guarantee, they do not have a very concrete polynomial time dependency there. I mean, which means that you might have a large degree in the polynomial, but they just didn't make it very concrete. In our case, it's much cleaner in the sense that our bound is at d squared over epsilon. So the polynomial degree is actually very clear in our work here. Second thing is that they require smoothness. They need to assume some Lipschitz continuity on multiple different things, and their bounds actually scale exponentially in these parameters. In contrast, our theory is almost independent of these, so it's okay for the smoothness parameter to grow as a function of the dimension. And finally, in their work, they have to assume exact score function, so they do not allow inaccurate score estimates. In contrast, in our work, we actually allow score estimation errors. There's another work by again Sutan, Xingho, and Jianfeng Lu and multiple their collaborators, and they have a paper called Probability Flow ODE is provably fast. They analyze a variant of the probability flow ODE, and the algorithm there actually has nice performance. But I need to point out that that algorithm is not really not exactly the probability flow ODE because they have to add an additional step in every iteration on top of the probability flow ODE iterations there. So essentially, it's like adding one more stochastic step in after every deterministic step there, and which sort of like make it closer to becomes a mix of deterministic and stochastic sample there. Also, they require some smoothness assumptions there, which we don't require here. And these are essentially the only two theory on probability of flow ODE before our. All right, okay, so I have maybe less than 20 minutes, so maybe I'm going to skip the proof strategy for the moment. So maybe let me just go directly to the second part, rather than just talking about the proof strategy. But before that, is there any questions from the audience that I should address for the moment before I move on to the acceleration part? Oh, there's a question.
So maybe can I ask a quick question?
Sure, yeah, of course.
So I see that the result you mentioned for the iteration x1 and y1, is there any maybe reason behind that? So why we cannot do
So
for
eventually
x1,
what you really care about is the x naught and y naught. But because of some regularity issue, actually characterizing x naught and y naught might, the theory might degrade quite a bit there. But because of, sometimes, for example, you start from like a more discrete type of distribution, but when you add the Gaussian noise there, the sum of the distance metric might be very, very different there. For example, like the KO or something. But if you just add a tiny little bit of Gaussian noise, which is what x1 is doing compared to x naught, so x1 is still almost the same as s naught, but we diffuse by the Gaussian a little bit. But in that case, the theory becomes much, much nicer, and actually also probably for practical purposes, also almost the same things.
Thanks.
It's a good question. Thanks. Yeah. All right. Okay. So if there's no further question, let me move on to the second part. About acceleration. So why do we care about acceleration?
Yuxin,
hey,
there was actually a question on the chat message.
Sure. Yeah. Let me see. Okay, so the question is, there is a question about, does it mean that minimizing the error between the Jacobians is more important? Let me give people a little more background here. Let me see. Oops. Okay, so I have made an assumption about the Jacobian. I think this probably is the reason that why we get this question about whether minimizing something related to Jacobian error is important. I will probably say this is probably not the most important thing because this is probably because we have to make assumptions on the Jacobian primarily because we are focusing on the total variation distance as a final metric. And for TV distance, like we can construct some strange counterexample to say that unless you assume something else like Jacobian proximity, you won't be able to have a nice results based on TV distance. However, if you're allowed to change the performance metric, for example, if you look at Watson size metric, we don't have result, but we sort of like believe that one will not require you to have Jacobian errors there because of the nice property about this Wasserstein thing, which allows you to sort of like move the probability density, in some sense. And at least in that case, the counterexample that we come up with is no longer important if you are thinking about Wasserstein distance here. So I would say probably Jacobian estimation error kind of assumption is mostly imposed because we want to have a nice TV distance type of bound or even KO bound. But in practice, this is probably not an important thing. Okay. Right. Hopefully this answers your question.
So I imagine that the question comes from slide 20, where theorem 1 has square root of D in front of score, but D in front of Jacobian.
Yes. So I believe that if we think about Wasserstein distance, we will not have any dependency on this Jacobian thing. And that's why I'm trying to say. But if you don't really want to have TV distance, in the worst case situation, I have to include this one. But for practical purposes, when you generate images, right, if you look at have small, for example, what's the sign distance might be good enough for practical purpose as well. So that's why I said probably this might be not be the most important thing. Score error is important, but the Jacobian one, not necessarily the most important. Okay. Does he answer the question? Okay, great. So I probably only have 10 more minutes. So let me just move on to the acceleration. At least let me just motivate it and tell you the results. So as you see, we have some iteration complexity guarantees. In practice, for example, like DDPM, it takes maybe 1,000 steps to converge. The thing is that every iteration, I need to access and evaluate the score function. And as I already said, score function in general is estimated using neural net and very large neural net in general. So which means that evaluating score function every time requires evaluating a large neural net, which actually could be slow. For example, as has already been mentioned in the DDIM paper, is that they say if your goal is to generate, let's say, 50,000 32 by 32 images. If you use DDPM, it will take more than 20 hours. But if you just use single-step GANs, it takes less than 1 minute. So there is a big difference between the sampling speed between GAN and DDPM. Even though DDPM might have a lot of nice thing in terms of the sampling fidelity, it might be very slow. So if you really want to generate a lot of samples in real time, this becomes a bottleneck for people. All right, okay. So now the question is that, can we actually find a way to significantly improve the sampling speed? And that has been a research lying at the heart of recent research in both theory and practice. There have been two different ways to think about acceleration that people have discussed a lot. One way is called the training-based algorithm. Training-based algorithm is the following. So now I have a diffusion process, let's say this DDPM1, which require you to access the score function 1,000 times. Now, based on this, what people are going to do is that, okay, let's try to do knowledge distillation. Let's try to say, come up with a another model, which can be executed much more rapidly, that can approximate the original diffusion model. So I try to learn another model to approximate this one, but hopefully this new model can be sampled much more quickly. And this has been a very active research area, and some of the state-of-the-art algorithm and consistency model is essentially things like this. This is one approach I'm calling training-based approach because this requires additional training phase. There's another approach called training-free approach, which is to say, okay, I do not want to look at a distilled model. I just want to say, just give me whatever that you already have, like the score function estimates, all right? I'm just going to change my sampling process, and hopefully, originally, maybe DDPM requires 1,000 steps. Hopefully, I can just use 10 steps to do the same, to achieve the same sampling quality. And that could be nice too. And this has also generated a lot of interest in the practical world. And in particular, this does not require any of the additional training. So this will be much easier to implement in practice because you just use whatever pre-trained score functions that are already there. No need to use a large, go to some large GPU resources to retrain different things. So our theory is going to focus on the training-free strategy because it's if you can do this, and it's going to be very appealing in practice. So since I already talked about the probability flow ODE, so now the next thing that I'm going to do is let me come up with a training-free accelerated version that can converge provably fast than the one that I have already presented. So this will be the first part. Now, how are we going to do this? Okay, so this is going to be a very high level description about what we are doing. Okay, again, we are working backwards. We start from the same random seed as the probability flow ODE, and then we adjust the update rule. every time I compute this yt minus, which is some deterministic function of my yt. I call it a middle point. This serves as a purpose for us to sort of like estimate yt plus 1. Actually, we can also just use yt plus 1 directly, but in theory, wise, this is a little nicer, a little easier for us to actually create this middle point. Now with this middle point, the next thing I'm going to do is to come up with things that directly use both yt and yt minus to create a new mapping here. Okay, so this is a very high level thing. Okay, and since this is yt minus sort of like represents our estimate of yt plus 1, this sort of like gives us a second order information. So I don't just use yt, but I use something more about yt. Now let me try to give you more precise expressions here. Okay, so if I only use yt, so in this site here, if I only use yt, this will be what original DDIM algorithm is doing. I use a linear combination of yt and the score function, and that is what original algorithm is doing. On top of this, I'm going to add some additional terms, and that leads to acceleration, which is something that looks in some sense like a momentum thing, right? This is like st yt, this is a t plus 1 and yt plus 1 in some sense. And this gives you a sense of some of the momentum thing. So it's sort of like a difference between the score function between the t's iteration and t plus 1's iteration. And it turns out that this kind of things provides a very nice way for us to make correction. So it corrects some of the bias term or some important terms there, which usually leads to acceleration. The good thing here is that even though we made a lot of modification here, if you look at what happens in each iteration, we evaluate the score function once. This is the first time and the second time. So I only access score function twice per iteration. So which means that you evaluate the large neural net twice, which is not much more than doing it for once. But you know, like, and then I can easily compute this, you know, update. Okay, so that is my accelerated algorithms here. Now, let me first show you some of the numerical performance just to convince you that this actually is doing great. So we compare it with the probability flow ODE algorithm with 8 function evaluations. This is the comparison between DDIM and our result. And this is for 10 function approximations. So you can see that our results, so both of them start from the same random seed. Okay, so you can see that our approach, even when you are just having like 7 or 8 functional evaluation, it's already achieved much better performance compared to the original. And this is a nice starting point for us to think about more about this algorithm. And we have also evaluated it not just on this church data set, but many other things. Basically, I forgot to say that we just use whatever pre-trained score function that have been already been made available on Hugging Face. And then we just use whatever, we don't use additional training there. We just use any pre-trained score functions there. And every time we are able to get better and less noisy images compared to the original. Okay. So empirically, this also has some advantages compared to the original. Okay, so now let me just quickly mention our theory, and then I'll probably just stop here. It's that with the same assumptions, now our theorem is going to look like the following. If we look at the TV distance between the x1 and y1, now the main term here becomes d to the 6th order over t squared. So if you remember in the probability flow ODE, we have 1 over t there. Now we have 1 over t squared there, which leads to provable advantages in terms of acceleration. So the iteration complexity now scales with 1 over square root of epsilon rather than 1 over epsilon in the original DDIM version. We still have all the nice property there. We have stability as in DDIM. We are able to accommodate general assumptions as previously. Okay, so these are all nice things. And we are also, our ongoing work is also potentially able to improve the dimension dependency to d to the fourth order to over t squared, which will make it, so d to the sixth is usually a little pessimistic here. We should definitely be able to do much better. All right. Okay. So in the interest of time, I'm probably not going to tell you more about the more theoretical interpretation here. One thing that I would probably just like to point out is that eventually, let me see. So I'm just going to mention one thing is that eventually one possible explanation about our acceleration is that we're using higher order discretization approximation in the presence of discretization. So we have to go to higher order approximation in order to make things speed up and make things more accurate when during the sampling phase. Even though our algorithm looks different from the DPM solver, which is a popular version in practice, actually intuitively, it has actually shared quite a lot of similar spirits there by going to a higher order discretization. So this DPM solver actually it's a version that goes to a higher order ODE in order to try techniques in order to solve a probability flow ODE. So our algorithm really shares some similar spirits as that. All right, okay. And finally, I just want to also mention that we not only have accelerated stochastic sampler, we also have stochastic accelerated, we not only have accelerated version for the deterministic one, we also have accelerated stochastic sampler, which are also in the slides just in case you're interested. So just to conclude, we have developed a new theoretical foundation for probability flow ODE in the non-asymptotic way. And we have come up with new schemes using higher order approximation, which allows us to achieve provable acceleration for score-based diffusion models. And there have been plenty of future direction that could be of interest for theorists. For example, how to achieve the optimal dependency on the problem dimension D, how to further accelerate it using even higher order approximation. Like, for example, in practice, maybe third order approximation is the best performing one in, for example, DPM solver 3. And most importantly, are we able to actually include the first score matching stage as well in order to develop full-fledged end-to-end theory that accommodates the entire diffusion model pipeline here. Okay, so that's everything I like to talk about today, and the results can be found in these two papers. Thanks all for your attention.
Yeah, thank you for very much for a fantastic talk. Does anyone have questions?
Oh, hi, Yuxin. I can ask a question.
Sure, yeah, thanks.
Yeah, thanks for the great talk. So in the first part, without the acceleration, you mentioned that the step size is exponentially growing and then it becomes like a constant after that. So can you give some intuition on why?
Yeah, so this is a great question. It sort of means that at the very beginning, in the forward process, at the very beginning, we don't want the noise to quickly corrupt the data information quickly. So we originally start from okay. So maybe let me come back to the okay. So this is about the beta t here. So beta t originally is taken to be extremely small, so that at the very beginning, it's not going to corrupt the true data quickly. Okay, but after you do it for sufficient amount of time, after like already, for example, lose half of the information content, after that you can sort of like make it much bigger and keep it flat to a much higher level. And then that will, you no longer really care about, how large these things are. The mathematical reason is the following. So 1 minus beta t sort of like captures the difference between the information between was the information changed within two adjacent iterations, which is this kind of things. Okay, this is one important quantity. There's one more important quantity is that if you think about xt, how much information is there? Which actually is some more complicated function. It's like a product of like 1 minus beta t. That's another thing. So that's like a signal to noise ratio at t's iteration. That is one quantity. Another quantity is the changes within adjacent iteration. And eventually, it's like it happens that it's the ratio of these two quantities that matters. And in order to control these two things, you have to sort of make sure that at the beginning, it's not decaying too fast. And after a while, everything is okay. So yeah, so this is probably not intuitive enough, but I just want to tell you originally there is some mathematical reason behind this. So.
I see. Okay.
But our theory is able to accommodate fairly general learning rate scheme. So you are able to come up with a learning rate scheme for many of the different choices. Now you just want to optimize it to find. This is one way to optimize it, but there might be other ways to optimize it as well.
Okay, I see. Okay, thank you.
Thanks.
Any other question? If not, I have some naive questions. So if you go to page 28, when you compare the pictures, I suppose that you the twice as many function evaluations are taken into account here.
Yes. This is eventually this is based on the same number of function evaluations.
Mm. Yeah. NFA and the number of function evaluations. I see.
Yeah.
And so the training based and training free. This is probably very naive question. Can you also combine the two so that like in other words?
First of all, you definitely can combine the two. That's one thing. But the training based one, people are trying to be very aggressive in the sense that let me see whether I have the slides here. Okay, so the training based one, the most recent work is called consistency model. So they actually, when they do this knowledge distillation, they want to make sure that they can do sampling in one step. So yeah, so it's called one-step sampling. So and since it's one step in, you no longer do further acceleration.
I see.
But it requires a lot of training, nice, carefully designed training strategy in order to achieve this. So they call it one-step sampling anyway.
I see. So is it right that you get actually better quality training from the training free approach, or
not necessarily because you are losing some information, not necessarily because well, okay, it's definitely faster after if you forget about the training part, additional training phase. Eventually, it's definitely faster because it's one step. Not necessarily, well, maybe close, but not necessarily the best sampling quality there.
I see. So like this in terms of the quality, training free approach might be
it's pretty good.
better. Yeah. I see. And another question was on page 37. Why is the third order optimal?
It's not optimal, but in practice, this is what they observe. Because maybe second order you need maybe 10 iterations. In third order now they need 2 or 3 iterations. And then when you have fourth order, you don't necessarily decrease the number of iterations, but you have higher costs there. So now this is a practical thing that they recommend. 3 seems to be a good number. In theory, I think you keep increasing the order, you get better and better performance. you know, there's also it probably depends on what kind of practical scenarios there, like also the dimension, a lot of different things. Yeah, it's
I
just
see.
like 3 turns out to be a good number for practitioners.
I see. See. All right. Thank you so much.
Thank you so much for
Yeah.
inviting me, and thank you all for coming.
Yeah. So all right. So then I'm gonna stop recording.
Bye, everyone.